So welcome all. In today's session, we learn about the LU factorization. We'll see some examples. So to start with, see in the last section we discussed some examples, and the question was, can we give examples of classes of invertible matrices for which the system Ax equal to b. Remember, the Ax equal to b was this system. So in before LU factorization, we were discussing how to solve a system of equation, and we developed Gauss elimination method. We saw some of its drawbacks, and then we developed what we call as modified Gauss elimination method. So we'll continue that discussion and we'll see what is this LU factorization and how does it fit into our picture. So we start with the system Ax equal to b, and the underlying assumption is that A is invertible, because in the last class we saw if A is invertible then this system has a unique solution. Okay, so to be very precise, this is our system. So this is our n cross n matrix. This is our n cross 1 column vector. So the question is, for which classes of invertible matrix A do we have a solution? The system is easily solvable. Easily solvable. By easily solvable means, see, in the last class we saw that there are techniques. For example, what we saw, the row operations in the Gauss elimination method to obtain a system of a solution. So the question is not whether or not this will have a solution, because since A is invertible, since A is invertible, AXB has a solution. It will definitely has a solution, and the solution is unique. And not only that, the solution is also unique. The solution is unique. So, and we know the solution is given by, the solution is given by x equal to A inverse B. So computing A inverse B is a very expensive business for a computer. Okay, So computing A inverse is an expensive business. This is rather, I would say, so the second question is, so this is precisely our question. Okay, let's not put it in the point form. So the question is, how easily can we solve a system of equation? So we start with examples. Example 1. Invertible diagonal matrix. Invertible diagonal matrix. So for example, if you have your A, now A is fixed, okay? If you have your A as A1, A2, if you have your A as A1, A2, An, now A is inverse and everywhere else this is 0. So on the diagonal there are entries. That is precisely what we mean by diagonal entries, diagonal matrices. And A will be invertible if and only if all these A1, A2, Ans are not 0, okay?
Hi, sir. Good afternoon.
Sorry?
So, good afternoon, sir.
Good afternoon, Thangeshwari. Good afternoon. So if I ask you to solve this system Ax equal to B, please mute your mic, Thangeshwaran.
Yes, sir.
Where did my screen go? Just a minute. Okay, what just happened? Yeah. So if I were to ask you this, what will be the solution of this system? That is A1, A2. If I am not writing anything, it means everywhere else it is 0, okay? X1, X2, Xn, and this is just B1, B2, Bn. Now can you tell me the solution of this system? You know what is this? This is A1, X1 is B1, right?
Yes.
A2, X2 is B2, and so on so forth. An,
Xn,
Xn is Bn.
Xn equal to Bn by N.
Yes. So all this, actually this, all this implies X1 is A1 inverse B1 and so on and so forth. Xn is An inverse Bn, correct? And you can take inverse. Why? Because all these are non-zero. So what we are doing, we are trying to see how can we solve the system more easily. In the last class, we saw that okay, Gauss elimination and modified Gauss elimination is one of them, correct? But to do that, we have to do a lot of computation, correct?
Yes, sir.
Yeah. So if A is an invertible diagonal matrix, you know the system has, anyhow if A is invertible, the system has a unique solution. In particular, when it is an invertible diagonal matrix, it is one of the easiest form of capital A in which you can find the solution in the most easy way. Okay. Now, if you remember, the one of the main goals of Gauss elimination method is to obtain a triangular form, right? In the last step, where we use the backward substitution and the forward substitution, if you remember, so it says that even if you have, see, having this capital A to be a diagonal form is not very practical, right? Not every matrix is diagonal matrix or can be written in a diagonal form unless and until it is diagonalizable. Okay, again, which is a very strong property for a matrix. But every matrix is a triangle. Every matrix can be put into triangular form. Okay, so we'll see if your A is, if your, let's say you want to find solution of this system Lx equal to B, where I'll just write the system elaborately. L is your L11 0 0 0, then L12, then L1n, it should be, oh I have done, yeah, this should be L21. So see, above the diagonal entry, above the diagonal everything is 0, right?
Yes, sir.
Now, if I ask you to solve the system, we can solve it without any effort, right?
Yes, sir. Diagonal elements. We can use diagonal elements only.
Sorry?
We can use diagonal elements only.
Yes. So first equation you read as L11x1 equal to B1, right?
Yes, sir.
So this will imply x1 is actually L11 inverse B1. And again, because since L is invertible, we know L11 cannot be 0, right?
Yes. Each diagonal entries are non-zero.
Exactly. So that is Lii is never 0 for all I, for 1 to n. Okay. So this much you know. Now what about the second equation? The second equation is L21x1 plus L22x2 equal to B2, sorry. So like this can be written as x2 1 upon L22 times B2 minus L21x1, correct?
Sir, correct.
Now see, you know everything here, right? Or yeah, yes. So L22 is a fixed number because L is given. B2 is again fixed number. The only thing variable which might seem is x1, but from first step we have already the value of x1, right?
Yeah.
Yes.
So you keep on doing that. You keep on doing that. And I don't know what equation it will be. Let's say if this is 1, it is 2. Then at some point you will reach n, right? Equation number n. And this will be ln1 x1 plus lnn xn bn, which will imply that xn is actually 1 upon lnn bn minus summation lni xi, I going from 1 to
N minus 1.
n minus 1. Okay. So again, see, even if you have a lower triangular matrix, the system is easy to solve, and the way we have solved it is called forward substitution. Okay.
Yeah.
Yeah.
Forward substitution. So if you have any doubt in the last, like if you have any doubt regarding this, please ask. Okay, the lectures are very long and we have enough time.
No, sir. No, sir.
Now example 3, this I'll do that. So this is invertible upper triangular matrix. Can we do this similarly as the last example?
Yes, sir.
Yes, sir.
Back substitution method.
Exactly. So if you have, let's say, ux equal to v, where this u is, you know what it is, u11, u12, u1n, u22, and unn, and here everything is 0. Okay, everything below diagonal is 0. So here you will have x1, x2, xn, okay. Now how will you solve it? You will use what we call as, and the reason should be clear, why one is called backward substitution and why one is called forward substitution. Okay, when we use forward substitution, the first value that we get is x1. Okay, and the values are attained in the order. First you'll get x1, x2, and so on when we use the forward substitution method. Whereas in the backward substitution, you will get the last value as the first value in the following way. For example, if you read the last equation, it will be unn xn equal to bn, correct?
Yes, sir. Correct.
So this will imply you just take xn to be 1 upon unn bn. Again, because we are taking invertibility of capital U, we know that none of the diagonal entries can be 0. Why? Because if any one of them is 0, the determinant of U will be 0, right? Determinant of a triangular
Matrix is
matrix is same as the,
Matrix
That is
not
not
dimensional.
no, if you have a triangular matrix, upper or lower, what is the determinant? Can I say it is the product of its diagonal elements?
Product. Yes,
Yes,
product
product
of
of
diagonal.
Yes. So from there it follows. So from if n equation you will first follow, then what will be n minus 1 equation? It will be un minus 1 comma n minus 1 xn minus 1 plus Okay. Then un minus 1 comma n is bn minus 1. Am I correct? Oh, just xn. Is this correct? So from here you can see that your value for xn minus 1, it will be un minus 1 comma minus 1 times bn minus 1 minus of this value. Is there any confusion?
No, sir.
Now you keep on doing that and you will reach the first place where you have u11 x1 plus so on and so forth u1n xn to be b1, and you will have x1 to be u11 just a minute, b1 minus, now tell me, u1j xj, j going from 2 to n, correct? It should start from 2, right? Am I audible?
Yes, sir. Yes, sir. I do.
So here you see you are going down and there you are going up. Okay?
Yes, sir.
Yeah. So far, consequently, if A is diagonal or triangular, triangular means either upper or lower, okay?
Yes, sir.
Invertible matrix, then the system Ax equal to B is fairly easy to solve, right? This we all will agree, correct? Is fairly
Yes, sir.
easy to solve. See, if you take A invertible, you know that anyhow this will be solvable. X can be, the unique solution will be given as x equal to A inverse B. So the question is not whether or not the solution exists. The question is how easily you can find the solution. Okay?
Yes, sir.
Because when you're working with computer, you know, like at each step error might happen. So you want to do your calculations in the most minimal way, in the sense that you don't want to do very much of computations. Even in real life also this you want, right? If I give you a matrix to solve, you will do it in the way such that lesser and lesser computations are involved. This should be the aim, right? So this is precisely what we are doing. Okay?
Yes, sir.
So now I give you an example. Okay. Okay, I'll give you example later. So remark actually. Remark is that not okay. Not every matrix is diagonal or triangular, right? So what to do? What to do? Do you get my point?
Yes, sir.
Secondly, we know that every matrix A can be written as A P inverse UP, correct? Where U is an upper triangular matrix. This you know?
Yes, sir.
Huh?
I know, sir. I know.
Okay. So see, so if you can solve the system for U, so what I want to say is the following. Let's say you have been given the system ax equal to b. Then this is true if and only if P inverse UP is x, right? Am I correct? In fact,
Yes, sir.
just a minute, sorry. In fact, you can replace it by transpose also. You don't need to go for T. P transpose UP, yes. Okay, because you're working with real. Now, see where P is such that P transpose is identity is P transpose P. Now, UPX will be PB, correct? So, now now this is a system, this is some system, right? X tilde is B tilde. This is easier to solve, correct?
Yes, sir.
This is easier to solve. And let's say you have found X tilde is this, B tilde is this. So if you have found a solution, when you find, let's say this is my system 1 and this is my system 2, when you find solution, the system 2, that is x tilde is b tilde, then using see what was x tilde actually, it was px, right?
Yes, sir.
So you can have your x to be p, you multiply with p transpose, so it will be p transpose x tilde. So you have a solution, correct?
Yes, sir.
So it might seem okay, this is much easier, right? Because we need to solve the system 2 and system 2 is in upper triangular form, right?
Sir, here P transpose is P inverse.
Yes, yes, see this is precisely what is written here.
Yes, sir.
This is called Schur's theorem, okay?
Okay, sir.
Yeah. So, but what I want, so this is just remark, okay? This is nothing to do with the what we are going to learn, but this is a quick remark. So it might be very tempting, you had a system Ax equal to B, we converted into a system number 2 which involves an upper triangular matrix, correct? Now we know the system with the upper triangular matrix is fairly easy to solve rather than as compared to any arbitrary matrix A. And when you find the solution of 2, we know what will be the original solution. The original solution will be P transpose times x tilde. So it might seem okay, we should do this, but see, finding P is a challenge, okay?
Yes, sir.
See, the whole point is to avoid the computation, correct? So finding P involves the computation of eigenvalues and eigenvector. And again, those eigenvalues and eigenvector, they are not easy to find using computer. Okay.
Okay, sir.
So this is the drawback. Okay. If I may write, this is the drawback. Theoretically it works, right? Theoretically it seems okay, this will be much better way. But why does it fail? Anyhow, if we wanted to do computation, we would have directly computed A inverse, right?
Yes, sir.
The whole point of learning this subject is to avoid computation.
Yes.
So if we were to use this method, by finding P, we would have originally done the computations of A inverse itself. It would have been much easier. Okay. So yeah, so so you should not be very much impressed with this method. This is what I want to say. Okay. Now comes the LU factorization into the picture. I will give one example, and because theory must have been covered in the class. So suppose that A is an invertible matrix. A is an invertible matrix such that A can be written as L times U. U is for some upper triangular matrix, okay? Upper triangular matrix, and L is for some lower triangular matrix. So A can be written as a product of one lower triangular matrix with an upper triangular matrix, okay? Now if I ask you to solve, then the system Ax equal to B, okay, it becomes, what does it become? Lux equal to B. Am I correct?
Yes, sir. Correct.
Yes. Now if you put ux will be some vector, correct?
Yes, sir.
U is an n cross n matrix and x is an n cross 1 vector, so its product will be n cross 1, right? So again it will be a vector. So let it be, let this be equation 1. We have, what do we have? Lz equal to B. Am I correct?
Yes, sir.
Now can you see that it is easy to solve because it is a lower triangular system, right?
Yes, sir.
Yes or no?
Yes, sir. Loyal triangle system.
So one can use forward substitution. One can use forward substitution to solve this system. Let's say 2. Forward substitution to solve the system given in 2. Now let's say you have a solution Lz equal to B. Now how can you recover your original solution? Your original solution is x, right?
Yes, sir.
So see, you have this solution. Now see, z is known, right? We have solved this system too.
Z is equal to L inverse
So this
B.
is a solution to 2. So it is given now, correct? First you solve system number 2, then you will have one solution which we are calling by z. Okay?
Yes, sir.
So now what is the only unknown thing is this? In number 3, what is the unknown thing? Only x, right?
Yes, sir. X only.
So can you use backward substitution now? Am I correct?
Yes, sir. Backward substitution because upper triangle matrix there.
Yes. So what do you think? Like so what does it says? If you can write A as a product of a lower and an upper triangular matrix, you know life is easier, right?
Yes, sir.
So this is precisely what is called LU factorization. Okay.
Yes, sir.
So we see one example and then we'll see, okay, it is not always possible to have the yeah, to have the LU factorization possible. So, okay, regarding this, so remark, what do you think? Is LU factorization always possible?
Uh,
No, it is always
no,
not possible.
no, sir. Yes, sir.
LU factorization need not be
Possible.
possible. Okay, for a given matrix A. Okay, maybe you can construct some example. Okay, so what do? We study the class, the classes of invertible matrices for which LU factorization is possible. Okay, now do you get some idea what we are trying to do? Is it clear? Do you have any doubt?
No, sir. No, sir.
Yeah. So do you want to, okay, let us first construct. Even I don't have any example right now in my head. Okay, let's say 2 cross 2. Okay,
Yes, sir.
A11, A12, A22, yeah, A21, A22. Okay, let us say LU factorization is possible in this case. Then what do you have? L11 0, L22, L21, correct?
Correct, sir.
Times U11, U12, U22 and 0.
0.
So what is this? This will be L11 U1, L11 U12. Remember A is given, okay? A is given. So you have to solve for L11, L21, L22, U11, U12, U22. Is that fine?
Yes, sir.
And here you will have L21, U1, 1 and some big term. Okay. Then how can you solve?
Equate the terms. What's it?
Sorry.
Equate the
Yes,
terms.
we equate, huh?
Matrix.
Yeah, so
Equate.
A11 is
L11,
L11 U11
U11, A12 equal L11, U12.
So this implies U11 is actually A11 L11, right?
Yes.
Okay. See, if A is invertible, then the L and U is also invertible, correct?
Yes, sir.
Why? Because see, determinant of A will be determinant of L times determinant of U.
Yes.
So all the diagonal elements of this L and U are non-zero. So I can take L11 inside, okay, in the denominator.
Yes, sir.
Now what does the second equation tell? A12 is actually
L11, U12,
L11,
U12.
U12,
So
right?
U12,
U12 has to be
A12
A12,
divided by L11.
L11. Now third is A21.
L21,
A21 is
U11,
L21, U11.
U11. U11 is equal to
U11,
A21 divided by L21. So
so this
now comparing 1 and
and
3.
this should imply A11 upon L11. It should be same as
A11 and L21.
A21 upon
A21 L21.
L21. Okay. So you can violate this condition, right? To construct one example for which LU factorization is not possible. Is it fine?
Yes, sir.
Just a minute. So can you give one example? Okay, we'll see. Okay. Now what about fourth? What about fourth condition? It says A22 is
L21, U12
L21 U12
plus
plus L22
U22.
U22. Okay. So you have values for U11, U12. So from here we can have U22, correct? U22 will be 1 upon L22 times A22 minus L21 U12. Am I correct?
Yes, sir.
I hope I am correct. So finally, if you write, your L was this L11 0, L21, L22, and what is your U? U11 is A11 by
L11. L11.
yes, A11 by L11. U12 is A12
L11.
L11, then 0. And what is U22? It is A22
1 upon L22. Okay.
yeah, and this should be same as okay. So here like you can have actually one condition on L21 also. Am I correct? What does it imply? That L21 yeah, sorry, okay, yeah. So is this correct? This, can you check whether or not this will be A1, the original matrix? It should be, right? because that's how we computed this whole thing, correct?
Yes, sir.
Is this clear to you, like what we have done?
Yes, sir. Clear, sir.
Yeah, so now if you take this example, for example, 1, no, a to 1 is, oh, for example, if you take this 0, then a to 1, yeah, God, what am I writing today? It is a1 2, but let's take 1 1 1. Is this an invertible matrix?
It's identical.
Is it in upper triangular form?
Uh, no.
No, right?
Yes.
Is it?
Yes, sir. No.
Yeah, no. So does it have an LU factorization? See, you check this condition, huh? Let's say this is condition star, okay, star condition. If this is L11, L L22 0, L21 and U11, U12. If this happens, right? If this happens, then what does it imply? Condition star. Can you tell me? Thangeshwaran, can you tell me what does condition star implies?
A1 is equal to 0.
See, the left hand side, because A11 is 0, so it will be 0, right?
Yes.
And you will have A21
1.
upon L21, correct?
L2 1. Yes.
So what does it imply? That
A2 1
A21
is
is
equal
also
to
0.
it's contradiction.
Huh?
Sorry.
But A21 is 1, correct?
Yes. 1 is equal to 0 contradiction.
Yeah. So this matrix does not have an LU factorization. Okay?
Yes, sir. Yes, sir. Yes, sir.
Yeah.
Understood.
So see, because the point is I didn't have any example in mind where LU factorization is not possible, but we can always construct one. Okay? The matrix A, when I did all this calculation with you, I wanted you to see how the thought process goes. Okay?
Okay, sir.
A is an invertible matrix, is it? A is an invertible
Yes, sir.
matrix.
A is invertible matrix.
Yes. So we have an example of an invertible matrix which has no LU factorization. Okay, so certainly the question that we asked in the beginning, does every matrix have an LU factorization? So this answer is no. Okay, so this remark
Yes,
is
sir.
correct. Yes?
The remark is correct.
Yes. So there is this theorem that you must have seen, okay, but I will not do that theorem. Okay, let me just write the statement of it. Do you know the principal minus and all those things?
Sir?
Do you know the principal minus? Okay, we will discuss it.
I don't know, sir.
So let A be an n cross n invertible matrix. So now this theorem will provide us some condition on A, some sufficient condition on A, such that A will have an LU factorization. Okay. So in general, what we have seen that invertibility does not imply LU, correct?
Yes, sir.
So if what if we add something, right? Invertibility plus something, then it might have LU factorization. Yes or no?
So why A invertible does not imply LU factorizations?
We just saw no this example.
Yes, yes, sir. Such your sir.
So we must add something, correct? To have an LU
Yes, sir. Yes, sir.
factorization.
Yes, sir.
This is this mathematical phenomena is same as like you went to a market and you saw a shirt, but that is not in your budget. Your pocket is not allowing you at that moment. So what the only thing is you have to add something in your pocket, correct?
Yes, sir.
So LU factorization is that shirt. Invertibility is the amount of money that you have right now. So what I'm trying to say here that you need to have more money to buy that shirt. Okay?
Yes, sir.
Yeah. So if you please stop me if you have any doubt, okay? Otherwise I can keep on going and going and going. I don't know. Such that so A being n cross n invertible matrices, it is an n cross n invertible matrix such that now this is the extra money, okay? This is the extra money after such that what I'm going to write such that all of its first n minus 1 leading principal minor are non-zero. Do you know the principal minor? Okay, we'll discuss, don't worry. So like this is the extra condition, okay? Just remember, can you see this condition?
Yes, sir.
Yeah. Yeah. Then A has an LU decomposition. Okay? A has an LU decomposition. You got the shirt, correct?
Yes, sir.
And not only that, with the shirt, okay, the shopkeeper was very happy with you and he said, okay, sir, you get one tie also. And what is the tie here? It is this, where this L is a lower triangular matrix with diagonal entries equal to 1. Do you get it? With diagonal entries equal to 1. So not only that, we'll have an LU factorization. Where is the LU factorization? Oh, we have not written. For example, not only that we have one LU factorization, these entries will be 1 also. Okay?
Yes, sir.
So now let us make you familiarize with what is called principal minor. You must be knowing it, you just don't know the term. That's it. So remember n minus 1 leading principal minor, okay? So example I should write in black. So are you getting the notes now, Thangeshwaran?
Yes, sir. I am getting notes, but your problem solving Google Meet link is not there, still not there.
This link, huh?
Yes, sir. Google Meet link is not there.
Can you put this link there?
Sir?
No, I don't know. I have sent this link to the authorities because I cannot put, I do not have access to edit that sheet. Okay.
Yes, sir, but so that no one is coming to the
But
class.
this is wrong, na?
Sir?
Nothing, nothing. Okay, you just focus here. So, what is the size of this matrix? 3. 3 cross 3, right? Now,
Yes,
hello?
yes, sir, 3 by 3 matrix.
Yeah. And so what does this theorem say? You put n minus 1 here. So, how many principal minor you have to find? So, principal minor, first I tell you, is the first thing this, then determinant of this, and the whole determinant. Okay?
Oh, okay, sir, okay, sir.
Now you know,
Now,
right?
now I know. Yes.
So, what is the first principal minor?
Determinant of A11.
What is it? A11, right?
A11.
First principal minor, it is A11. What is second principal minor? It is determinant of A11. A12, A21 and A22. Okay, determinant of this.
Yes, sir.
And you know the third principal minor also, right? The determinant of A. So I just write third principal minor is actually determinant of A. Now what does this theorem say? What does this theorem say? Now you just read the statement very peacefully, okay?
Yes, sir.
A is an n cross n invertible matrix such that all of its first n minus 1 leading principal minors are non-zero. Then A has an LU decomposition. See, if A is an invertible matrix, then the nth leading principal minor is also non-zero, correct?
So one more time.
Sorry?
So once again.
What I am trying to say, if you want to apply, for example, this theorem, what does this theorem say? A has to be invertible, first of all, which means determinant of A has to be non-zero, correct?
Yes, yes.
So this has to be non-zero. Now it says all of its first n minus 1. What is n minus 1 here? 2, right? In this
Okay.
example.
2 by 2 matrix.
So which means this has to be non-zero
Yes, sir.
and this has to be non-zero. If this happens, then A has an LU decomposition, correct?
Yes, sir.
So yeah. So in this example you see the first principal minor was not non-zero, correct?
Yes.
So this example also says that converse of this theorem is not true, correct?
Yes.
Converse not true. Okay, so if you have any doubt then please ask, and this is called Doolittle's factorization. Okay, I write here, this is called Doolittle factorization. Is it fine? Like, do you understand it now? Like, what do we mean by LU factorization?
Yes, sir, I understand. No.
Yeah. So, if I give you one example, can you find its LU factorization? Example, 1, 1, minus 2, 1, 2, 1, minus 1, minus 2 and 1. So first of all, you check what is the first principal minor?
1.
1, right? What is the second principal minor?
1.
1. And what is the determinant? Is it non-zero? So you compute the determinant of A. What is it? 1, 2 plus 2, 4, minus 1, 1, minus 4, then minus 1, then 1 plus 4. Then 4 minus 3 plus 3 minus 5. It is 2, right?
Yes, sir.
So it is not 0. So because all we have to first check whether or not this is invertible, right? The very first thing in all this business. Okay. Now I will denote first principal minor by M1. Okay. What is M1? First principal minor. What is it?
1.
1, right? I will write here M1, M2, M3. And what is M2?
1.
1. So can I say thus A has a Doolittle factorization, right?
Yes.
So we know now. Oh, Doolittle meant yeah. Oh, sorry, it's double O. Yeah, sorry, I'm really sorry. It's Doolittle.
DWO.
Yeah.
Yes.
So A has a Doolittle factorization. So like why do we have this theorem? Do you know? Because see, before even starting with the factorization, if you know, okay, indeed this has a factorization, life will be much easier, right?
Yes, sir.
For example, if I give you a matrix and you start doing all these computations, but it does not have an LU factorization, so this is nothing but a waste of time, correct?
Yes, sir.
So that is why these existence results are very important. Now, what does what does Doolittle factorization say? It precisely say that this matrix 1 1 minus 2 1 2 1 minus 1 minus 2 and 1. Yeah. So this can be written as lower triangular, right?
Yes, sir. Lower triangle and upper triangle matrix. We can count.
But it has a special property. What is the special property? 1 here, 1 here, 1 here, right?
Yes.
And it will be second row first column, third row first column, something like this it will be, correct?
Yes, sir.
And here you will have u11, u22, u33, u12, u13 and u23. Now we can solve this, right? Can we solve this?
First matrix, how diagonal entries are 1?
From the Doolittle factorization. See, it says L is a lower triangular matrix with diagonal entries equal to 1.
Oh, yes, okay, sir. Okay,
So
sir.
this is a special, that is why it has a name, Doolittle factorization. Okay.
Okay, sir. Okay, sir. Now clear.
Yeah. So this is precisely what I was saying. You went to buy a shirt, you had the money The shopkeeper was very happy and he said, okay, now you can buy another shirt. Okay?
Yes, sir. Yes, sir. Okay, sir.
Yeah. So now can you solve it?
Yes, sir. We can solve.
So how do you do this?
We have to find all the
Yeah, so let us do that, okay?
constants.
So
L2, 1,
u11, u12, u13. It will be, first row it will be like this. Then you will have u2, u11, l31, u11. Then you will have l21, u12 plus u22.
L3, 1.
Then you have l21, u13 plus u23. Here you will have something big, which will be l31, u12 plus l32, u22.
L3, 1, U13, L32,
Plus.
U3.
So this is going out of matrix, but I hope that is fine. Working with iPad is good because of this only. I can always shift. Yeah, tell me. Plus L32, U23.
U23 plus U33.
See, as you can compare it directly, I'll copy this matrix and plug in the values, okay? Copy, paste. Yeah, so U11 is 1, right? You just compare, right? Is this fine?
Yes, sir.
See, oh, here it will be minus 1.
Minus
No,
1.
that is not fine. Is this step clear?
Yes, sir. Clear.
Now you can remove all these U11, right? Because it is 1.
Okay.
So what does it give you? L21 is?
L21 is 1.
Yes. Yes. But about L31?
L31 minus 2.
Oh, let us not do this way. Yeah. Okay, so I'll write this. Okay. It is 1 and it is minus 2. Correct? Is this
Yes,
correct?
sir. Yes, sir.
Yeah. And here you will have U13 is minus 1, so you will have minus here, minus L21, minus L31, U12 you can remove, so you will have L21, L31. So if you solve this, can I write directly? What is L32? L21 oh this is L21, okay, this is L21, so this is, we have already figured out that this is 1, so U22 has to be, come on tell me, U22 has to be, see these are some calculations going on before you, please tell me what should be the answer. Thangeshwaran, are you there?
Yes, sir.
Yeah, L21 is 1, just see the pink line, okay, L21 is 1.
Answer is 1, sir.
Huh? Okay, you just check after doing all this calculation, because see diagonal elements were 1, right? Now what is L21? L21 we have here, from here it is 1, correct?
Yes, sir.
So I will put 1 here and minus 2 here.
U22 is equal to 1, sir.
Exactly, U22, so let us just write U11 is 1, u12 is 1, u13 is minus 1. Here everything is 0. Now you are saying u22 is also 1, which is correct, right?
Yes, sir.
And what about u23? See, you can use this also. This is also minus 1, right? Because L21 is 1. So what is u23?
-1.
Yes, minus 1. So now only two entries left. L31 and L31 is also given, right? This is minus 2 and u22 as you are saying is 1. So what should be L32?
3, 2. I think 3. 3, sir.
3, yes, 3. Okay.
Yes, sir.
So now only one entry is left. U33. You just put this value. L31 is minus 2.
So 2.
Then plus L32 is 3. U23 is minus 1 and U33. All this value has to be equal to 1. Correct?
Yes, sir. So here it is +2, I think.
This will be
First
3.
+2.
6 it should be, right? What should be the value? Tell me please. Minus 2, minus 3.
0, sir, I think. First term is 2. L31 -2. So minus L31 equal to 2.
3. Oh, okay, directly we should, because only one entry is left. Yeah, right? This should be equal to the original matrix. Original matrix is 1, 1, minus 2, 1, 2, 1, minus 1, minus 2, 1. Now you please tell me. From here you can tell, right? 2 minus 3 plus x is equal to 1. So it will be minus 1 plus x. So it should be 2, right? Is this correct? You just check, okay? You take your time and you just check whether or not this matrix multiplication is fine.
Okay, sir. Okay, sir. I'll check.
Yeah. I'm giving you some 2-3 minutes. Just multiply LU and you just see whether or not you are getting A.
Yes, sir.
Oh, you are getting, right?
Yes, sir.
Okay.
I think.
Yeah, so this is called the Doolittle's factorization. Now let us solve this system. For this system, let us solve let b equal to 1, 1, 1. Can you solve this system? So what do we have to solve? What is the aim? To solve ax equal to b, right? Where we have seen in the above how to solve this kind of system when you have LU factorization. You just write A as LUX equal to B, correct?
Yes, sir.
And put this UX to be Z. And you will get LZ equal to B. Now you can solve this system, right?
Yes, sir.
So solve this. What is this system? 1, 1 minus 2, 0, 1, 3,
3.
0, 0, 1.
Z1, Z2, Z3.
Okay. Z1,
Z2, Z3.
Z2, Z3.
1, 1, 1.
Yes.
So,
Just a minute. So 1, 1, 1.
Z1 is equal to 1.
So you will use forward substitution, right?
Yes, sir.
So it will imply z1 equal to 1, then z2 equal to 0, right?
Yes, sir.
Because you will have z1 plus z2 equal to 1, which implies z2 equal to 0,
Z3 is equal to 3.
and minus 2 z1 plus 3 z2 plus z3 equal to 1. So this will give
3.
z3 to be 3, right?
Yes.
So hence just a minute. So hence what does it imply? Z is actually 1
0,
0
3.
3. Now is the answer complete?
No, sir.
No, because see, this was step 1.
Yes.
Or let me write it as step 1. Now step 2. Okay. Now step 2. So which system you have to solve now? Ux equal to z, right? Am I correct?
Yes, sir. Correct.
So what was u? U was this. I am writing u, okay? U was 1. Okay, 1 1 minus 1. So this was u, right?
Yes, sir.
1 1
0
minus
1. 1 1 minus 1, 0 1 minus 1.
1 1 minus 1, 0
1
1
minus 1.
minus 1, and I think 0 0 2, right?
Yes.
Now
X1,
x1,
X2,
x2, x3.
1, 0, 3. Equal to
1 0 3. Now quickly tell me the value.
X3 is equal
So
to
which
3 by
method
2.
will you use first? Backward substitution, right?
Yes, sir.
So
X3 is equal to
x3 will be 3 by 2.
X2 will be minus 3 by 2.
No. x2 will also be, see, x1 minus x2 minus x3 is 0, right?
Yes, X2 minus X3, yes.
So this implies x2 is actually same as x3, right?
Yes, yes. Okay, sorry.
Yeah. And third is x1 plus x2 minus x3 is 1, right? So this implies
X1
x1 is
1.
1. So the final answer is
1,
so
3 by 2, 3 by 2.
yes. So isn't it a much easier method? The final answer is for computer. I mean, I know again the solution, the system has to be, this again there is some computation, right?
Yes, sir. There's some completion.
Some this computation,
Yes.
but this is nothing compared to raw operation, correct?
Yes, no, not using raw operation.
Yeah. So how many equations are these? These are some 9 equations. That's it.
Yes, 9 equations.
9 equations, that too very easy. Okay. So
Yeah,
this is
yes.
one method which we one existential result which we call as the Doolittle's factorization method.
Okay.
Okay.
So, Doolittle mathematician name?
Yes. Yes. It's a
Yes.
mathematician's name. Now we will use Cholesky's factorization method. So the aim of today's lecture is to get you familiar with what do we call as the factorization method. Okay.
Yes, sir.
Why is it called a factorization method? For example, if you have some number 6 is 2 times 3, then 2 into 3 is a factorization of 6, right?
Yes, yes.
So in the same way, when A is LU, so this is LU factorization. Okay, we are factoring A into two lower triangular and upper triangular part.
Yes, sir.
Okay. Now one remark. LU factorization is not unique. Okay. LU factorization. Can you tell me why? See, if you have some LU factorization, okay, then you can multiply it with some diagonal matrix also, correct? Like D inverse D. Will it make any difference?
No.
Right. For example, you can choose your D to be this diagonal matrix D1, D2, Dn, and each of them is non-zero. Okay.
Yes.
Now, if you take LD inverse times du, so if you multiply a lower triangular matrix with a diagonal matrix, it will again be a
Diagonal matrix.
lower triangular matrix.
Yes, lower triangular matrix.
And what about du? It will be an upper triangular matrix.
Yes.
So see, you have another factorization.
Another decomposition. Yes.
So the factorization is not unique by any chance.
Okay. Okay.
But we don't need uniqueness, right? To solve, do we? We just need one LU factorization, right?
Yes.
You just need one LU factorization to make your life easy. I hope this is clear what I'm trying to indicate here. That uniqueness is not important.
Yes. Uniqueness is not important.
Existence is important.
Yes.
Now, do you know positive definite matrix by any chance?
I don't know clearly.
Okay.
But little bit I know. I think three minor matrix sign we have to compare.
Okay, let me just write.
Yes, sir.
A matrix. Okay, let me just put it here. A matrix A, actually symmetric, you know, right?
Yes, sir. Symmetric.
A equal to A transpose. ठीक है?
Yes, yes.
A symmetric matrix A, which means A is same as A transpose.
A transpose.
Is said to be positive definite if something happens. Okay, this X transpose AX. So see, A, okay, L, you know, if X is an n cross 1 vector, right? I want you to, realize that this definition, because it is not clear with many people. Why is this definition? So X is n cross 1 vector and A is n cross n. So what will be the order of X transpose? It will be
n by 1.
No, 1 cross n, right? Not n by 1. We are taking transpose.
Okay, sir. Okay, sir. I understand.
Now, what is the order of this as a whole?
1 by 1, sir.
1 by 1, which means it is a
Singleton.
Singleton, what does it mean? 1 by 1. It is
single element.
Real number, right?
Real. Yes, sir.
Yeah.
Yes, sir.
So this is a real number.
Yes, real vector.
So I can check whether or not real number is positive or not, right?
Yes, sir.
So it is said to be positive. It is said to be positive definite if this is greater than 0 for every non-zero vector x. Okay? Do you get it?
Yes, sir.
See, why this, before this positivity you should ask. You should ask yourself, why are we able to say it is positive? At least before that it should be a real number, correct?
Yes, real number.
Now you know why this is a real number. I hope, because this I have seen many people don't know. Why are we able to compare? These definitions are not made in heaven, okay? These definitions are made with certain logic. Now, so tell me what is not clear in this definition, then I will move forward.
Sir, how? I am also confused, sir. Just
What is the confusion? You just check whether x transpose Ax is positive for every matrix or not, okay?
okay.
Okay, I'll give you one example.
So,
Whatever. Yeah.
so suppose one value is real value is positive, then positive definite. Matrix A is positive definite.
No, for every x, this value should be positive. This value should be positive for every x. See, for every non-zero vector x, okay?
Okay.
So, for example, if you take A to be identity, okay? You are taking A to be identity. Then what is x transpose Ax? It is just x transpose x, right? Yes or no?
Yes, sir. Yes, sir.
Now, if your x is x1, x2, xn, then your x transpose will be here, right? It will be x1, x2, dot 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 xn, correct? Yes or no?
Yes, correct.
Now, can you multiply this and tell me what will be the answer?
x1 square plus x2 square.
Yes, x1 square plus x2 square up to xn square.
Xn square.
So, if you have chosen x to be non-zero, then the square has to be strictly positive, right?
Yes.
Because if x is a non-zero vector, which means it will have some xn which is non-zero, right?
Yes, sir. That's for sure.
So this will be strictly positive. Strictly positive. Right?
Yes. Yes. Any non-zero value is strictly positive.
Any non-zero value strictly positive? What are you saying?
Each entry is x is r.
Yes. Yes. The only possible way it can be 0, this x transpose x, is if this is 0, right? x1 square plus x2 square, blah blah blah. If this is 0, right?
0 vector only.
Which means all of this has to be 0 because square, this is sum of squares, right?
Yes, sir.
But this cannot be possible, right?
Yes.
Because x is chosen to be a non-zero vector.
Yes, non-zero vector only.
Yeah. So I hope this is clear.
Yes, sir. Clear, sir. Now clear.
So can I say identity matrix is a positive definite matrix?
Yes, positive definite.
I is a positive definite matrix. Now what about, okay, let me give you one more example which is not identity. What about, you just tell me, okay? What about this matrix? Can you check whether or not this is positive definite? So what do you have to do? What do you have to do? You choose, you first choose any arbitrary x, right?
Yes.
Arbitrary x equals to x1, x2,
So,
which is not 0.
yes, sir.
Then compute x transpose ax. It will be x1, x2, 1, minus 1, 0, 2, x1, x2. Okay. Now can you tell me the answer? It will be x1 minus x2, then 2x2, correct? Yes or no?
Yes, sir. Yes, sir.
Now it will be x1 square minus x1 x2 plus 2x2 square. Now you tell me. Before even checking that, is asymmetric? Is asymmetric?
No, sir.
Hangeshwaran?
No, sir.
So this cannot be positive definite, right?
Oh,
See,
okay, sir. Okay.
yeah.
Suppose A is symmetric, then it's positive.
Then, okay.
Okay, sir.
So let us put minus 1 here now. I will give you one easy characterization. Okay, don't worry. Minus 1. Now this is symmetric, right?
Yes, sir.
So see that this is the thing, see the definitions very clearly. Now tell me what happens. So this will be minus, yeah. So you will have one minus x1 x2 term extra, correct?
Yes, sir.
Now what is it? It is x1 square minus 2x1 x2 plus 2x2 square, correct?
Yes, sir.
Can I write it as x1 square minus 2x1 x2 plus x2 square and then plus x2 square, right?
Yeah. So x1 minus x2.
Now tell me, will it be strictly positive?
X1 not is equal to x2.
Yeah, so make two cases, right?
Yes.
Case 1, if x1 is equal to x2, which means both of them are non-zero, right?
Yes.
So then it will become, the next transpose x is nothing but x2 square, which will be strictly positive.
Positive. Yes.
Yes.
X1
Second is x1 minus x2 is,
not equal to 0.
what does it imply? That this implies
First
x
term,
transpose,
first term positive, second term maybe
second term
0.
it can be anything, we don't care now, right?
Yes.
See,
Second term maybe
because
0.
yeah, but definitely it will be greater than equal to x1 minus x2 square, right?
Yes.
And this is strictly positive
Yeah.
because x1 is not x2.
Yes, sir. Yes.
Okay.
Sure.
So then we know that this is a positive. This is positive definite. Okay.
Yes, sir. This type of competition is not comes to my mind suddenly.
Yeah. See, that is the thing. Okay, I will give you one test directly to check whether or not A is positive definite. Okay.
Okay, sir.
Let A be n cross n symmetric matrix, because first we need symmetric matrix, right?
Yes, sir.
The following are equivalent. Do you know this term, TFAE? Okay, then the
following
following are
equivalent.
equivalent. It means TFAE, short form. Okay,
Okay,
the
sir.
following are equivalent. Number one, A is positive definite. Now you will see this principal minus, they play a very important role. Okay. Number
Okay,
two, all the principal minors are positive. Okay. See, this is the second time the principal minors have come into picture, right?
okay, sir.
Now, for example, if A is a positive, if I give you this theorem, okay? Hello?
Yes, sir.
Yeah, okay, let me give you one more characterization. All the eigenvalues,
Are positive.
yes, exactly. So all the principal minors are positive, which means the nth principal minor will also be positive, correct?
Yes.
But what is the nth principal minor?
Determinant of
Exactly, exactly. So let us, like if A is A11, A12, you know, A1n, A21, A22, A2n,
A1 up to A1.
then K principal minor, K principal minor is denoted by nk. It will be determinant of, you just take first K submatrix, okay?
Yes, sir. A KK
The determinant of this,
and
okay?
it's positive.
Yeah. So what does remark say? I'll write few remarks. You will say whether or not you agree or not. Okay.
Okay.
First, okay. Let A be positive definite. Okay. Now you know principal minor and all those things are positive. Okay. A be a positive definite matrix. Correct.
Yes, sir.
Now, can I say then A is invertible?
Nth minor is non-zero.
Yes. Yes. Because nth principal minor,
Yes.
which we are denoting by what? Mn. It is
Determinant
determinant
of
of it and it has to be strictly positive.
yes.
Or you also see from this theorem, if all the eigenvalues are positive,
So
then you know determinant is the product of eigenvalue, correct?
yes.
So
So determinant positive.
yeah, so that also you can see. So now can I say that Ax equal to B? Okay, let me say, given non-zero vector, given a vector B, the system Ax equal to B has a unique solution. Can I say this?
Yes, sir.
Why? Because it is invertible, right?
Yes, sir. Not even matrix has unique solution.
Yes, because See, some new definition is being introduced. So we are just seeing how does it fit into our system, okay?
Yes, sir.
Now, can I say that A has an LU factorization?
No, first I think first minor, all the minors are non-zero, then only say LU
So
factorization.
if it is strictly positive, which means it is non-zero also, right?
Yes, yes, all minors are strictly positive.
See, this theorem, what does this Doolittle's theorem? We have this theorem, right?
Yes,
They all of its first n minus 1 leading principal minors are non-zero. This we
yes,
want.
yes,
And positive definite says that okay, not only principal minors are non-zero, they are also strictly positive. Right?
yes, yes,
So, in fact, LU factorization, so this is true, right?
yes, sir, yes, sir.
Because all the principal minors are positive, hence non-zero, correct?
Yes, sir.
So this is really important that so consequently all this thing is to say I'll write it in red. Yes, Thangeshwaran, you raised hand.
Sorry, sir, mistakenly.
Yeah, so can I say I'm just writing one thing, okay? Consequently, every positive definite matrix has Doolittle's LU factorization. Can I say this?
Yes, sir.
Don't just say yes. If you believe in this, then only say yes. Is it clear? Like why? Why is it true?
All principal
What
minors
was
are
the condition? Okay, let us go back to that theorem. What is the condition? First condition is A has to be invertible, correct?
yes,
And every positive definite matrix by definition it is invertible, yes or no?
yes,
Now, what is the second condition for Doolittle factorization? All of its first n minus 1 leading principal minors are non-zero. And this
same.
condition is satisfied by a positive definite matrix, correct?
Yes, sir.
So, by this theorem, which is appearing on your screen, we can say that every positive definite matrix has Doolittle's LU factorization.
Yes, sir.
Yes, okay. But one thing you should note, okay? See,
Suppose
Thangeshwaran.
some,
Yes, yes.
suppose some principal minors are zero.
Sorry.
Suppose there exists some principal minus of 0, then what will happen?
Then it won't be a positive definite matrix, okay?
Oh, okay, then okay.
Thus, we are just dealing with positive definite matrix.
Yes, sir, yes, sir. I understand. That's my question only.
Yeah. So let us say you have A to be LU, okay?
Yes, sir.
Now tell me if you take transpose, what will happen?
L transpose, U transpose L transpose. Okay.
Yes or no?
Yes, sir, yes, sir.
No, but A transpose is same as A, right?
Yes,
Because A is positive definite, so A is symmetric, correct?
yes, It's positive definite and A is symmetric.
So if it is positive definite, then by definition it is symmetric, right?
Yes, definition as per definition.
So what should be then L? You know, you can compare these two. Idea, okay?
L transpose equal to U transpose.
L transpose or L.
L transpose equal to U.
So can I say what you are saying? This suggests that we may get L to be or U to be L transpose. Yes or no?
Yes.
Yes, correct. And that is precisely what Cholesky's factorization gave us. Okay?
Yes, sir.
See, all these things, they have a history. Okay? So what I'm trying to do here is to make you realize how these things come into the picture. Okay?
Okay, sir. Okay, sir.
When you will see the Cholesky's factorization statement, you will understand what I'm trying to say. So if A is an n cross n symmetric positive definite matrix, symmetric positive definite matrix, then then A has a unique, now we'll have a unique factorization. Okay, then A has a unique factorization A to be L transpose. Okay, so above we saw that intuitively U should be L transpose, right? Intuitively we see here that U
Yes,
should be
sir.
L transpose, correct?
Correct, sir.
So this is where this theorem says our intuition is correct. Okay,
Yes, sir.
this
Yes,
theorem
sir.
precisely says that okay, your intuition is correct.
Yes.
So
Yes.
where L is a diagonal matrix, oh sorry, L is a lower triangular matrix, lower triangular matrix with positive diagonal elements. Okay, we know why it should be positive diagonal elements, because A is positive definite. Okay,
Yes. And the
so
positive eigenvalues.
yeah, so you see, if you know, I'll write just one remark with this theorem.
Sir, I have one doubt.
Yes, please ask.
Suppose eigenvalues, some eigenvalues are negative, then the determinant value is positive.
No, but if
That
some
is,
eigenvalue is negative, then it is not a positive definite matrix. Okay, all the
no,
eigenvalues
no,
have.
even number of eigenvalues is negative.
But this says, the theorem says, this theorem says that all the eigenvalues has to be positive. Okay.
Oh, okay.
Yeah.
Okay.
Yes, please ask.
Yes, sir. I understand. This theorem tells that.
Yeah. So A is a positive definite matrix. Then we know A has two decomposition. One is, let's say, you know, this LU, which is Doolittle's factorization. Okay. Is that fine? This we know, right?
Yes, sir. Yes, sir. I know.
And secondly, we have A is some LL transpose. Okay, where this is coming from Cholesky's factorization. See, what I want to say, the L in the Doolittle's factorization and the L in the Cholesky factorization, they can be different. Okay.
So Doolittle factorization does not mention about uniqueness.
Yes. So
So
Cholesky factorization say whenever you can write positive definite matrix as L times L transpose,
yes,
then, and if you are able to write, let's say L1 L1 transpose, okay,
yes, sir.
then L1 is has to be same as L.
L,
Okay.
yes.
Yeah.
Uniqueness.
Uniqueness in that sense. Okay. So now you know this positive definite matrix is a very strong condition, right? Because it gives us a very beautiful LU factorization.
Okay, sir.
The proof is, I think it's big.
Okay.
Do you want me to do the proof?
No, sir. I will refer the book notes.
Okay, if somehow you are not able to do that, then you just tell me, okay?
Yes, sir. Yes, sir. Sure.
So should we do one example or mm, just a minute, huh? Just a minute. Just a minute. Let me do something. Okay, let us try this example as the end. Okay, then we'll finish. Example. Let A be one, 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 two. Now tell me, is it a positive first of all, is it symmetric? Is it a symmetric matrix?
Yes, sir. Symmetric matrix.
Is it a positive definite matrix? You just compute all the principal minor.
F is positive determinant.
So it is a positive definite matrix, right? So which means Cholesky's factorization we can do, right?
Yes.
So okay, let us compute. Okay.
Okay.
So it will be L11 0, L22, L1 L
L to 1, sorry.
L11 0, L21, L22. Am I correct? Is it correct? Are you there? Am I audible?
Screen not received. Okay, sir. Okay, sir. Now received.
Now, can you tell me what is this? This is precisely L11 square, then
L
L11
1
L21,
L 2 1
then
L 2 L 2 1 L 1 1 L L 2 1 square L 2 2 square. Okay.
so you remember in the Cholesky's factorization, L is a lower triangular matrix with positive diagonal elements. Can you see this written on the screen?
Yes, sir. Yes, sir.
So which means this L11 and L12, L22, these are positive, right?
Yes, sir.
Yeah. So can you tell me the value of L11? It is going to be 1, right?
Yes.
Then what is the value of L21? It is also 1.
Yes.
Now this L21 square plus L22 square, it gives you 2.
Yes.
So what should be the value of L22? It should be 1,
Yes, 1. Okay.
right?
Yes.
So Cholesky's factorization it is actually क्या होगा 1
0
1 0 this will be my L, right?
yes
such that A is L transpose, right? Note
yes
that
sir.
note that you can choose L dash to be, or let's say L1 to be, you can choose -1 -1 -1 0 also, right? Because L11 square from here was 1. Okay, why this 1 came into the picture? Because L11 has to be positive, but this
Yes
was
sir.
for Cholesky's factorization. In general, it need not be true.
Yes sir.
Then what I'm thinking is this, L21 is -1 certainly, and you can also choose L2 to be -1 0 1 -1. Okay, then you can find that you can write A as to be L1 L1 transpose. It is same as L2 L2 transpose. Okay, is that fine? Is that fine?
Yes sir.
Now, okay, I know I'm see. So this is Cholesky's factorization. Now in the end, let us do the Doolittle's factorization. Okay.
Okay sir.
So what do we need in Doolittle's factorization? We need A to be LU. That is A is
L
A is what? A here is 1 2 1 1.
yes 1
L here is 1 1 and then something,
1
right?
L to 1. Okay L
Okay, L 2 1. And then what about the upper triangular? We don't know, right? U11 0,
U
U22.
U to 1.
Yes. So now
Sir
if you
U
do this calculation, then can you tell me?
sir I think U to 1 sir.
Oh, okay. Yeah. Oh, no. This is upper triangular, no? So we should have it here. Okay.
Yes, U1 to okay okay.
So what it be the answer will be? It is U11, right? U12, then L21 U11,
Okay. L to
L21.
1 U1 2 plus U to 2.
Now quickly tell me the answer. So you can compare.
U1
U11 will be 1,
1 U1 to 1
U12 1, right? So here you will have 0. So if you
L
compare this
L to 1 1
1 and
U2 to 1.
1, right? This is same as the Cholesky's factorization, right?
Yes.
Yeah. Okay. So yeah, but remember that they can be different. Okay. So if you have any doubt, please ask. I think this was computationally high session, right?
Yes sir.
Yeah. Okay, if you have any doubt, please ask. Otherwise, we can end this meet.
No sir, no doubts.
Okay, then we'll see you maybe next time.
Okay sir. Thank you sir.
Yes, yes. You can leave, Thangeshwaran.
Yes, sir.
So with this, we have finished the various LU factorization methods for a given system of equation, that is Ax equal to B, where A is an invertible. So we saw what do we mean by LU factorization, and in this particular direction we saw that LU factorization for a given invertible matrix need not always be possible. There are sufficient conditions such as given in the Doolittle's factorization method, when all the principal minors has to be non-zero. In particular, when all the principal minors are positive, when A is an invertible symmetric matrix, we have more than one factorization that we call as Cholesky's factorization. And in that particular method, we saw that uniqueness is always there in the sense of the factorization. So with this, we finish this session. Hope to see you again.